So I want to explain how you can, if you are used to those formulas and those concepts, actually end up also doing non-cumulative geometry by changing your point of view. So as you all know, there's a way to decompose a function in terms of the Schrödinger representation in terms of time frequency shifts in this way, and then Gabor came up with the idea, let's not take all points from the phase space, just take a discrete set, and for example, let's take the lattice alpha c times beta c, and then the question is for which g's and h can you do this, and this leads you to the problem of deciding when pi alpha k beta lg is a frame. And then the very nice thing is that these Gabor frames have this extra way of representing things. So you have the Janssen representation that if you go from your lattice to the adjoint lattice via Poisson summation, then you can write every f in this form where you have this interchange between f and h. And that's going to be a crucial point when we later talk about non-cumulative geometry, because that's something that they are very used to. They have a whole formalism adapted to that. But for applications, very important, because in the adjoint setting, you don't have to take the inner product of f with the system, but you have h with the system on the adjoint. And it has turned out to be useful to have nice functions g for which the whole theory works. And it turns out that either you work with Feichtinger's algebra or the Schwarz cluster, and everything is always nice, and you are in a nice setting. And it will be also crucial for what I'm going to talk about. So one of the few examples of the main results, like the density theorem, that if you have a frame, then the density has to be less than equal to 1. And the result by Becker that you have actually tight Gabor frames for every lattice. And that uses phenomenal algebras. And using this approach that I will explain, these results you will see how operator algebras fit in and actually allow you also to prove these results, but actually also to prove it for like nice function like in S0 or Schwarz class. And the other thing is that I will talk about later is the Balian-Low theorem, that you can't have nice Gabor systems or orthonormal bases at the critical density. So what are the key tools for doing time frequency analysis? You have the Schrödinger representation, and for the continuous case you use that it's projective irreducible representation. So projective means every time that you compose things, you end up with an extra phase factor, which is really important, which we will see later. Gives you the twisted convolution, which is a crucial thing in this whole business. But if you restrict it to a lattice, let's say this lattice alpha c times beta c, then you actually just get a reducible representation. So you get something non-trivial in the commutant of your algebra generated by those time frequency shifts, and that's going to be the reason why you have this nice structure. And so what people call this matrix coefficients the short-term Fourier transform, and if you prove it from this point of view, then you see that S0 is just a set of integrable vectors, and the Schwarz space is the set of smooth vectors for the Schrödinger representation. And for proving this reconstruction formulas, you either in the continuous case need Moyal's identity, so this orthogonality relation for the short-term Fourier transforms, or if you use Poisson summation formula for the symplectic Fourier transform and look what the symplectic Fourier transform of the product of two such things is, and then you realize that the
corresponding lattice that you get to your given lattice is this adjoint lattice, then in this way you get what's called the fundamental identity of Gabor analysis, and that's precisely the relation you need to write down the Janssen representation. And as long as you're in this nice class of functions, like everything is like in S0 or in Schwartz, then you can do this. And so usually, as we all have seen before, in both cases you have operators associated to it. You have to your system associated a coefficient operator, which just is this taking the short-term Fourier transform or restricting it to the lattice. Then a way of synthesizing things. So you start with your system. You build a new function, or like here, like the same in the discrete case. And then for studying if it's a frame or not, that's turned to be useful to have these frame operators. And so everything can be encoded in this way. So now, on the next few slides, I would like to move from the system acts on G to operator algebras. And so for this, we start recollecting building operators. So we build superpositions of time frequency shifts in the continuous case or the discrete case. And then we actually want to have like nice operators. Let's say A is in L1 or in Schwartz class. And I will indicate this by A1 and A infinity. A infinity will be like a smooth version of your operators. And we know that if you take like, you have these assumptions, then you get actually trace class operators, and everything is very nice. So if you complete those these classes of operators, then you actually get, as an inner closure, then you get the compact operators. But using this way of representing them in terms of this Schrödinger representation, you end up with the Moyal plane, what's called the Moyal plane. And you can do the same thing in the discrete case. And if you do it in the discrete case, then this A infinity is known as the smooth noncommutative torus and was first introduced by Kohn in his work on noncommutative geometry. And then A1 turned out to be useful for time frequency purposes, and has appeared in Janssen's and Gorchnik's work and so on. And if you take the norm closure for this algebras, then you get what's called the noncumulative torus, and that's basically the main example of a noncumulative manifold in noncumulative geometry. And so people in noncumulative geometry, they are more interested what these algebras do, kind of representation theory and so on. And the funny thing is, you have to do the same kind of business like you're used to in time frequency analysis to actually understand those algebras. And so now here is the crucial observation that you just rethink what the synthesis operation is doing. So before you always thought that this collection of things and then you synthesize it. Now you let this operator A of C, pi of C, the superposition, act on something. So in this way you let like this subalgebras of the compact operators act on functions in S0 or Schwartz, and this will again give you a Schwartz function or a S0 function, and similar in the discrete case. So by rewriting what the synthesis operation is, you end up looking at operator algebras. And the next crucial thing is that that if you take the analysis operation, so as you for these coefficients, these A's, then you actually end up with a very nice structure. You actually get an inner product, but an inner product with values in these operator algebras that I just introduced. And so that's the first observation, and it's even better. So it's really what you would think of an inner product in the Hilbert space case. So if you take the adjoint in the algebra, and now here you have to take it with respect to this twisted convolution. So you have to take this into account, then taking this star means just interchanging f and g. And the other thing is, we had this action before. So if you plug in this action into this inner product, you can pull it out, which again amounts to like a twisted convolution of this sequence A that gives you the operator with VGF. And everything is nice. So if you take operators in your respective classes and your f and g's in S0 or Schwarz, you get these relations, and you also can show it's a positive operator and precisely 0 when g is 0. And in this way, you also get like frame operators can be viewed as like rank 1 operators with respect to this inner product, to this operator valued inner product. And this can be really made precise, and that's the theory of Riefel and Paschke. So if you have every time you have such a setting that you have a vector space with an operator valued inner product and an action on it, you can actually show that this. So you take the operator norm of your function as of this inner product ff, and take the square root. This really defines a norm, and if you complete your space with respect to these norms, then you get a Hilbert-Seastar module. And so what we actually just showed is that if you do this, we get that S0 or the Schwarz space are Hilbert-Seastar modules over the Moyal plane and the Noncumulative torus. And the next thing is, for understanding what those Moyal planes, the structure of those algebras is, Riefel observed that you have to actually use what's called Morita equivalence. So you want to have a second algebra that fits with the first Hilbert-Seastar module structure. So you want to have a second module structure on your spaces S0 and Schwarz, which is compatible with the first structure. And so in the case of the Moyal plane, that's very nice and very easy. You just view L2 as a right C module. So the complex numbers are a Seastar algebra, and so that's okay. You just view it in a different way, and if you do this, then you have this as your inner product GF, and the same for the Noncumulative torus. But for Noncumulative torus, we use that we have this adjoint lattice and the operator algebra associated to this adjoint lattice. And then it turns out that if you pick this inner product, this gives you the right Hilbert-Seastar module structure. And the very important thing is, and that's every time, it's even for general Seastar algebras, but every time you're in the setting that you have a module with two structures with an inner products that are behaving in this way, then you call them Morita equivalent. And what we have actually, if you use what we just with these definitions, this is the reconstruction formula that I wrote down in the beginning for the continuous case. And if you do it in the discrete case, then you get Janssen's representation. That's just looking at Janssen's representation in this setting. So what we have shown is that the compact operators are Morita equivalent to the complex numbers, and that this operator algebra given by alpha c times beta c is Morita equivalent to this one. Oh, there should be alpha and beta. And so this is also equivalent, and that was observed by Riefel, because it shows that K has only one irreducible representation. Is equivalent to the Schrödinger, to the Stone von Neumann theorem about the uniqueness of the Schrödinger representation. That's the same statement. And so what we have now shown is, using that we have this inner product, thanks to results by Riefel, that shows that those modules we have actually a very nice structure. They are finely generated and projective. What does this mean? It means you can write every element in a S0 or Schwarz as a finite superposition of rank 1 operators. And these are just frame operators. So this is in the continuous case. You can actually show that you just need one, but that you don't get out of the theory. You just get it in this particular example. And for the Gabor case, you get multi-window Gabor frames. So in this way, and you can also interpret this as standard module frames for these Hilbert-Seastar modules. That's the theory that Frank and Larsen developed like 15 years ago by extending Hilbert space theory to Hilbert-Seastar modules. So in this case, it's the same thing. For Gabor frames, you can also view it as standard module frames for the corresponding operator algebras. And the nice thing about those projective modules are, and those multi-equivalent Seastar algebras, and that's what people in operator algebras care about. They care about projections. And so there's a nice way of getting projections. So if you have this inner product on the right-hand side, and you can show it's the identity operator, then you actually know that if you take this element GG in the other algebra, it's a projection. And it's actually if and only if. So in this sense, if you do this and then if you look at those projections, then you get actually other ways of looking at your modules. And if you do this for the Moyal plane, then this condition was an L2 condition. So this just means that this is normalized as norm 1 in the L2 sense. But in the noncumulative torus case, it means that GG for this other inner product is the identity, and this is precisely the Wechsel-Rath condition. So that's precisely for G to be a tight frame. So what you get is that there's a correspondence between constructing a projection in noncumulative torus and tight Gabor frames. Yeah, and so using this picture, you then can show that you can have nice multi-window Gabor frames, and that you can have nice Gabor frames with one generator. And it also gives, in this way, constructions of projections in noncumulative tori, in higher dimensional ones. So if you do this in the two-dimensional case, then this was actually done first by Riefel in '81. And if you look at his paper, he uses the rotation algebra picture, which amounts to the walnut description. And in his construction of this projection, he actually constructs the first painless non-orthogonal Gabor expansion, Gabor frame. So that's, but using this framework. So now we will exploit this connection between Gabor frames and tight frames a little bit more. And for this, I will briefly tell you why people came up with noncumulative geometry. So they look at commutative Seastar algebras, and they turn out to be just continuous functions on some compact space. And so what Swan in the 60s observed is that if you take continuous sections of a vector bundle over a manifold, then it's actually a finally generated projective module over these continuous functions. And so Riefel took this and said, replace here Seastar algebras, this commutative by general Seastar algebra, and say, if you have a finally generated projective module, it's a vector bundle over this algebra. So the Hermitian structure comes from a Hilbert-Seastar module valued inner product, like in the continuous case. And the smooth structure comes from nice subalgebras of this Seastar algebra. So what we just have, what in our setting this amounts to this algebras A infinity and A1. So these are our smooth subalgebras, and we actually have now shown that we have actually vector bundles over the Moyal plane and the noncumulative torus. What you now can do is you want to do some differential geometry, so you want to have some derivations that on your algebra, and then you want to be able to say what is a covariant derivative, and it's a mapping on this module which satisfies this property, the left-Leibniz rule. And then you also want to have compatibility condition, that if you take the derivation of fg, it's inner product nabla fg plus f nabla g. So let's try to find out. Okay, and then you call this a gauge connection if they are compatible connections. If you have two compatible connections, then you can define the curvature. And if this is a multiple of the identity, you call it a constant curvature connection. So then you can move on and put a complex structure on it, like in complex analysis. You take d1 minus I, d2, and d bar. Then you can look what is the Laplacian, and then you do the same thing. Every time what you do something on the algebra, you also do it on the module structure. So you do the same thing for the connections. You get the connections nabla, nabla, bar, and you call a vector holomorphic if nabla bar g is 0. So that all sounds very abstract, but now let's see what this means in this particular cases. So derivations for this Moyal plane are you take this operator and multiply it by x, and then you have this extra phase vector 2 pi I. And you do the same thing with the omega component, and then you can show if you take the standard representation, the standard operators that you get for the canonical commutation relations, like multiplying with 2 pi I t and taking derivatives, that this actually define connections if you view the Schwartz space as a line bundle over the Moyal plane. So you can really check that that's really trivial. It's all trivial, and this is really just this relation that people use a lot in time frequency analysis. But it just means that this gives you compatible connections, and the commutation relations, the canonical commutation relations, tell you that this gauge connection is actually of constant curvature. So in this way, you get a gauge theoretic interpretation of the canonical commutation relations. And then you can play around a little bit and look what these operators d and d bar and nabla, nabla bar do. And then you observe that, oh, you get the creation and the annihilation operators for nabla, nabla bar. That you get, if you take the Laplacian for the connection, you get the harmonic oscillator, the Hamiltonian of the quantum harmonic oscillator. If you take nabla, nabla bar, you get the Hermite operator, and the holomorphic vectors are precisely the Gaussians. So, for example, if you look what d bar does on the inner product, and it's precisely multiplying it with 1 plus x squared plus omega squared times VGF. So if you now take some LP norms of this Laplacian acting on an inner product, then you end up with modulation spaces. So that's one way of getting to modulation spaces, defining norms on this operators. And so you can do the same thing in the discrete case. You multiply with k and you with L, and this are your derivations. And you can also write down connections, and again you get constant curvature connections and analogous for the adjoint lattice. And so it might look like why should these connections be important? But if you look at the proof of Battle of the Balian-Low theorem, it's precisely this Leibniz rule for one-time frequency shift that's used. So in the proof of the Balian-Low theorem, so which says that if you have functions in L2 that they're nice localized, which means that the connection it should be nabla 1g plus nabla 2g is finite, then you can't have an orthonormal basis. So it's precisely, for example, also for the Schwartz functions. What does it actually show? And then if you go further in the proof, what people use for Balian-Low is this contradiction to the canonical commutation relation. But that's just this is a contradiction because we have a constant curvature connection on this Hilbert-Seastar module. So in other ways, if you phrase it in terms of of non-convex geometry, it says there are no smooth line bundles over the smooth non-convex torus. So that's Balian-Low's theorem, and that's something people are not aware of in non-convex geometry. And so now we have all those projections, and now I want to briefly talk about some joint work with Dabrowski and Landi, where they actually found a way to classify those projections. And they said, oh, let's do like a Dirichlet type energy on those space of projections. And so they wrote down, and here you take the trace of for the Seastar algebras. And then they wrote down this energy functional. Then they really did like first variation. They came up with some Euler-Lagrange equations. But then they observed something very important, that this functional is actually bounded below by the first conjugate number of your line bundle. And so then using this, when this is equality, they came up with a first order equation for for these critical points of this functional. So these are really non-commutative harmonic maps. So that's, and so if you do this in the case of those projections that we have, you end up in the case of to check a condition nabla bar G, so a generalized eigenvalue function for this setting, but this lambda is not a complex number. It's usually an operator in a Seastar algebra, which is Moretti equivalent to the given one. And in the case that we have either that this is a complex number because k is equivalent to c, and then you get that those g's are precisely the Gaussians that is satisfied this. So, and if you write down this energy functional, in this case it amounts to minimizing this, and in the discrete case you end up with this equation, but here now you have an element in the adjoint lattice. And so that's where people were stuck for 10 years, and that's where our cooperation started. They asked me, can you solve this equation? And if you know Ron-Shan duality, then you realize, oh yeah, we can solve this, but you need to use Ron-Shan to solve this equation. And so in this way, you get that every tight Gabor frame satisfies such an equation. So these are precisely the minimal points of this energy functional. So that's a different way of viewing tight Gabor frames is as energy as critical points of this functional. Okay, thanks.
Thank you very much. It shows that there are very nice connections, unexpected connections, which are just at the beginning of exploration, as far as I understand, between non-commutative geometry and Gabor analysis. And it's also clear now that the bridge is going both ways. I mean, both sides are learning from each other. Sorry for my comment first, but questions?
Well, yes, you expressed your theory in terms of the usual old modulation notation from time frequency analysis. If you use the Wigner formalism instead, do you get some interesting symplectic symmetries?
Yeah, you can do the same thing also in this case. Yeah.
But do you get anything extra from that?
You get, yeah. If you what the next step is, of course, now you study operators like pseudo-differential operators on these line bundles, and then I guess it would be useful to you do it in the Wigner setting. Yeah.
Thank you.
Further questions or comments? If not,
next step will be the fine group. AX plus.
Yeah, I mean, in a continuous case, you can do this. You can I can write down, for coming from the orthogonality relations, I always can write down that this one Seastar were generated by the representation is Moretti equivalent to C. That's no problem. But the discrete version, I don't know how to do this. What's the dual object? I'm not sure.
good. Thank you very much. And